Welcome to MEI Modelling with Algorithms. We're on the topic Linear Programming 3, Application to Network Problems, and this is video 3.1, Shortest Path Problems. Now, the idea in all of the remaining videos actually is that we're going to return to some of the problems that we talked briefly about earlier in the course, and we're going to show how we can convert each of those, or think about each of those, as an optimization problem which can be tackled using linear programming. And now that we've got technological tools available to us for solving problems like that, it's going to make the job of doing this kind of thing in practice very easy. So this is the first problem we're going to look at. We've got a very simple example here, a very simple network, and suppose we're trying to find the shortest path from A to D. Now, we already know about Dijkstra's algorithm. We could do it that way, but what we're going to see in this video is how we can cast this as a linear programming problem and solve it that way instead. So the first thing to say about this is that even though this is an undirected network, in the context of shortest path problem, we know, for example, whether AB is in the shortest path or not, we're only ever going to be going in that direction. It's impossible, if we're going from A to D, that the shortest path would ever involve travelling from B in the direction of A. So, to all intents and purposes, then, the arc AB is directed. We can certainly think of AB being a directed arc within the context of this problem. Likewise, AC, BD, and CD. However, BC, it's possible that this could be traversed in either direction. So we've got to think of this as, well, probably think of it as two directed arcs, one going from B to C and the other going from C to B. So if we think about it, if we're going to have a variable for each arc that describes whether or not that arc is going to be included in the shortest path or not, then we've got 6 variables here. Alright, so each of these arcs, which we are going to think of as being directed arcs, will have one variable associated with them, and this one here, which is really 2 arcs, one in each direction, so there are 2 variables associated with that, so it's BC or CB. So we're listing, when we're writing an arc down, like AB, that order is important. So if I write AB, I mean going from A to B. If I write CB, then I'm going from C towards B, and so on. So what we'll do is we'll say, well, these 6 variables, each one of them can take only one of 2 values, either 0 if it's not included in the shortest path, or 1 if it is. So that'll be the same for all 6 of those. And because these values can only be 0 or 1, we'll sometimes refer to these as being binary values. It's worth saying as well that we're using AB, the symbol AB, to represent a variable. Obviously we could use X, Y, Z, etc. like we've done previously, but it's going to make things easier if we just stick to this notation, so it's always clear which arc is being referred to. Now, because we're trying to find the shortest path, this is going to be a minimization problem. What we need, of course, then is an objective function, such that it will be minimized when we have the shortest path. So we're going to write down an objective function that will give us the length of any path according to the values of the variables that are telling us whether each arc is in the path or not. So if AB is on the shortest path, then that will give us a contribution of 2. If it's not in the shortest path, then it will give us a contribution of 0. So if we write 2AB, 2 times the value of AB, remember AB is only either 0 or 1, so if AB is 1, then we'll get a 2 added to our objective function. If it's 0, then we'll get nothing added to our objective function. Alright, so we're going to do the same thing. So each arc, we're going to multiply the variable associated with that arc by the weight. So 2AB plus 4AC and so on. like that. And then what we also need are the constraints. Now, to work out the constraints, we need to think carefully about this. So for a start, we know that because we're dealing with a single path going from A to D, we'll be starting by leaving node A. So either we'll leave along AB or we'll leave along AC. So what that means is that the total of the variable AB and the variable AC will have to be exactly 1 at all times. Okay, so we can only leave A using one arc, and that means that AB plus AC must equal 1. Alright, then if we turn our attention to node B, well, we can only enter and leave B once. So if we enter B along one arc, we're going to leave B via another arc. Now, the possible arcs through which we could enter B are going to be AB and CB. So the first thing we'll do is we'll write down each of those. So that's AB plus CB. So one of those things will be 1, the other one will be 0. And then when we leave, we'll be leaving either by BD, and if we do, then that will have a value of 1. So if I subtract that, then I'm either going to have 1 added there and then 1 subtracted there, or 1 added there, 1 subtracted there, or I could leave along BC. So if I subtract BC as well, then one of these will be 1, the other will be 0, one of these will be 1, the other will be 0, which means that overall this thing will have to equal 0. So really what that's ensuring, it's not so much that we can only enter and leave B once, but that we will enter B and we will leave B. So these are arcs which enter B, these are arcs which leave B, and we guarantee here that we will, for every time we enter B, we will also leave. Now, of course, because this is a minimization problem, it's going to minimize the shortest path. In reality, we're never going to find a path that's entering B and leaving B more than once. So it's not quite that this constraint is forcing that to happen, but the fact, combined with the fact that it's a minimization problem, that will definitely happen now that we've made that requirement. So we can do the same sort of thing for node C. So we have the two arcs which are entering C potentially, and then the two which are leaving C there. And again, if we require that total to be 0, it will ensure that if we enter C, we will also leave C. And finally, turning our attention to node D, again, we can only arrive at D via one of these two arcs. So if I add those two together, the variables corresponding to those two together, so that's BD plus CD, that will have to equal 1. So to summarize all that, then we have our objective function, which is based on the weights of these arcs multiplied by the binary variables. So that will give us the weight of any path. And then these are the constraints, and these basically ensure that what we have is actually a single path from A to D. And remember that these variables are quite restricted in the values they can take. They must take values of either 1 or 0, so they're binary variables. And just one more thing on that point, because this is a minimization problem, even if you just say that these variables have to be non-negative integers, that will actually be enough for this to work, because it's never going to choose to make one of them more than 1, even if it could, because it wouldn't then minimize the length of the path. So if you were, say, using a piece of software that can't handle binary variables but can deal with integers, then that would be sufficient for solving shortest path problems. So what we'll do then, of course, now we've formulated the problem, we'll put it into a software package that we can use to actually solve it. This is what's been done by Lindo. You can see here where we've typed that in. You should recognize that format now from the video that we saw on Lindo, and this is the output. And the main thing to look at here firstly is the value of the objective function. So that's telling us that the shortest path has a weight of 5. And then if we look here at the variables, we can see they're all either ones or zeros. The ones that are ones are the arcs which are included. So we can see here the arcs which are included are A, B, C, D, and B, C. There we are, and clearly it has found the shortest path. Now, of course, in this problem, it was quite a simple problem. We didn't really need to use software to do that. We could do that ourselves by inspection. But the point is, if you had a very large network, you could still apply the same process, and then the software would tell you the shortest path, even if it was something that would take quite a while to do by hand. So, for example, here's a slightly more complicated network. We're not going to do the whole thing here. I just want you to think about these two questions. So if you were formulating this in the way that we've just seen, how many variables would be needed? Remember, of course, that some of these arcs you will be able to treat as directed arcs and others you won't be able to. And how many constraints are going to be needed? Pause your video for a moment and see if you can work those out, and then I'll reveal the answer. So in terms of the number of variables, well, we can treat any arcs leaving A as directed and any arcs arriving at F as directed, so they will have one variable each, totaling 4, and then these ones, 1, 2, 3, 4, 5 of them, they will need 2 each, giving 10. So the number of variables that are going to be needed is 14. Now for the constraints, well, again, if you remember what we saw effectively last time is that every single node has a single constraint associated with it. So we've got 1, 2, 3, 4, 5, 6 constraints. Of course, they're not all the same type. The constraint at A and the constraint at F will look different because they'll give a total of 1 than the other 4, but the total number of constraints is 6. Of course, that is assuming that we're not counting the constraint that the variables are binary. So, you know, depending on how you want to think about it, you could argue that there are a further 14 constraints on each of the variables. But in terms of the constraints that come from the actual network problem itself, then the answer is 6. So that concludes video 3.1, shortest path problems. The next video will be 3.2, longest path problems.